Writing equations. We already know how to translate words into expressions. So if an equation is made up of two equal expressions, we just need to learn what the equal sign will look like in words. The word is in a sentence often tells us where that equal sign will go. That's our clue. Is in a sentence can be thought of as short for is equal to. So then you know that's where the equal sign goes in your equation. So let's look at some examples. The first example we have is Tim is 5 years older than Kathy. Write an equation for Kathy's age. So we're going to first write the equation in words, very similar to how the process was done for writing expressions. We'll write the equation in words, and then we'll translate that into a mathematical equation using numbers and symbols. So think, how can you represent this problem with numbers and symbols? Why would you choose certain variables to represent certain values? What are the operations that will happen between those variables that are happening to the values in the sentences? Is there more than one way to represent these expressions and therefore equations? These are all things we have to think about when we go about this process. So first, translating the equation into words, we have Tim. So we can be more specific and say that it's Tim's age. So then we have is, and again, that's our clue. There's the clue that that's short for is equal to. And then we have 5 years older than Kathy. So again, we'll be more specific. We're talking about Kathy's age. And when we say 5 years older than is you're adding 5. So that's going to be plus 5. So 5 years older than Kathy is going to translate to Kathy's age plus 5. So we have the translated sentence, the words written as an equation in words. It's being more specific. It's helping us define the symbols and the variables and numbers we're going to use. So now let's do just that. For Tim's age, we'll use a capital T. Is equal to, that's our equal sign to make it an equation instead of just two expressions. And then Kathy's age plus 5, we'll use a capital K and then the plus symbol and 5. So Tim is 5 years older than Kathy. The equation for Kathy's age is T equals K plus 5. Now let's look at this example. Bob is 4 inches less than twice the height of Fred. Write an equation for Bob's height. So again, we're first going to write an equation in words from these sentences and then translate that into a mathematical equation. So for Bob, we'll be more specific, and we're talking not just about Bob's weight, not Bob's eye color, not what shirt Bob is wearing. We're talking about Bob's height. Then we have is. There's that clue word to is equal to, right? That's what it's short for. That's what we can think of. And then we have 4 inches less than twice the height of Fred. So we want to think, what is happening here? We have the height of Fred, and we have twice the height of Fred. So we can think that that's multiplying by 2, or that's doubling Fred's height. And then we have 4 inches less than. So less than is telling us subtraction, but we have to now switch the order. So even though 4 inches comes before twice the height of Fred, because of the less than, we're going to switch the order and first have double Fred's height, and then we'll subtract, so less 4. From that, more easily, we can now go to the symbols and numbers. We can have Bob's height using a capital B is how we'll represent it. Is equal to, that's our equal sign, making it an equation. And then we have double Fred's height less 4 is 2 times capital F minus 4. So Bob is 4 inches less than twice the height of Fred is in an equation. B equals 2F minus 4. Let's look at this third example. Here we have speed is the distance traveled in an amount of time. So again, translate that word into an equation using words, and then translate that into an equation using mathematical numbers and symbols. So speed, that's very specific. We're talking about speed. Is the is equal to. That's short for is equal to. And then we have the distance traveled in an amount of time. When we have something in an amount of time, you can think that's being divided up by the time. It's a whole, and then we're creating different parts, so we can think that's the distance divided by time. That's the operation that's happening. So now using symbols, we have a little lowercase s for speed, is equal to is our equal sign, and then distance divided by time, we have a little lowercase d divided by, we're using the fraction bar, and then over little lowercase t for time. So speed is the distance traveled in an amount of time, can be represented with the equation s equals d over t. And this equation actually has all variables. There's no constants or coefficients here other than 1. So we can really break down this equation and look at it more using a table. So let's use this table here to find some solutions to the equation s equals d over t, where again, s is representing the speed, and we're giving it a unit now in meters per second. D is representing the distance in meters, and t represents the time in seconds. So we can see here again the equation s equals d over t, or d divided by t. So we've entered the distance traveled here in this left column, and the time it took to travel that distance in the second column. So we can see different distances, different meters, and different times in seconds. So we can use the equation s equals d over t to find the speeds and fill in that blank column. So we know that if s equals d over t, we're dividing the first column divided by the second. So for that first row, if we have a distance of 39 meters and a time of 3 seconds, that would be a speed of 39 over 3. That would give us 13 meters per second. The second column, again, we're dividing the values. So 65 over 5, 91 over 7, 36 over 4, 54 over 6, and 90 over 10 will give us the values for that third column. And here you can see we've done just that. So we've simplified, we've actually found those quotients, and we can see that we have the first 3 rows all have a speed of 13, even though there were different distances and times. And the last 3 rows all have the same speed, even though there's different distances and times. So it's interesting to see the patterns that come from the equation and that relationship of speed equals distance over time, and how the solutions compare to each other. Even if the variables are all different, you can even get the same solution. So lots of different things we can see when we start to use tables and look at the relationship it has with an equation and different missing pieces in a table.